Hello and welcome back. So now that Steve has created our floor digital asset and our stage digital asset, it's time to focus on something just a bit more interesting. In this video, we're going to begin the construction of the talented ball himself. So this is our character. Now this character is not going to be as sophisticated as you'll find in such amazing movies as Shrek and Nemo, etc. He's just a ball, but we have spiced things up just a bit. This ball is going to sport his own little rig so that we can control squash and stretch easily. He's also going to sport his own custom shader. So in this video, we will start with the super complicated modeling process, which I believe is just laying down a sphere.
Yep.
After doing that, we're then going to spend the rest of this video focusing on the construction of a very simple custom shader. Now, why are we doing this? Well, we can obviously just jump right in and use a Vex super material. And with that Vex super material, we saw that we can control the diffuse color. We can select what kind of specularity we would like as the end result from our lighting model. We can assign a diffuse map, so we can use a texture to drive diffuse color. All that stuff is built in. But the shader itself, the material, it's kind of heavy. It sports a lot of parameters that we're not going to need to use. That's number one. Number two, do we really want to just keep using the Vex super material over and over? I like the whole concept of learn something new in every video if possible. So I think this would be a fantastic time to introduce the construction of a simple shader. So that's what we're going to do. We're going to first jump over here to our whiteboard, and we're going to begin with the modeling process. Let's just all stipulate that Steve has dropped a geometry container, and he's named it something like character. And inside of that, he's going to create the geometry, our sphere. Little does this guy know, in the near future he's going to be climbing ladders and jumping off diving boards and performing for crowds. All right, so with this, we're just going to take the output and run it into a material. In the material node, we need to make reference to some sort of material. Now, back in the Houdini Fundamentals class, we took a bit of time to talk about the differences between materials and shaders. So a shader is what's responsible for calculating a bunch of different things. For if it's going to be a surface shader, it's going to calculate all of the lights that's striking the surface at this particular location when it gets rendered out, and it's going to worry about coming up with the color that will be used for that pixel. We also have displacement shaders so that we can add new geometry at render time. There's all sorts of things. We can volumetric effects, etc. But the shader is the guy responsible for those calculations. A material is a node that can contain one or more shaders. Generally, it's simply a material that we are going to apply to our geometry. But it's inside the material. So if you were to open its hood and look up underneath, that's where you'll find one or more shaders, and they're the guys that are responsible for doing the actual calculations. So I want you to keep that in mind, because in this case, we are going to create our own material, and inside that material, we're going to create our own custom shader. So how do we go about doing that? Well, we all know that working at SOP level, we're going to drop a manager down that's going to manage our shop networks. So this is going to be our standard shopnet. So we'll jump down into our shop network, and inside here, instead of creating the Vex super material, which is what we've done every time up to this point, both in fundamentals and in this particular class itself, Steve is going to create a material node. Now the material node is just a container, and inside that container, you can start creating shaders. So let's see, how do I want to draw this? So let's just do arrows, and these arrows are going to indicate that we're talking about being inside of this particular node. So inside of our shopnet, we're going to create this material node. And the material node, it's a container as well. It's a container that holds shaders. So if we jump down inside of it, you're going to find that we already have one node there. And that node is responsible for taking out whatever you construct inside of it. So it's going to be called sub-output. So I'm just going to draw a little node right here and put S.O, sub-output. And he's going to be looking for some sort of connection coming in. And this connection is going to be from our shader that we're about to create. So what kind of shader are we going to create? An empty one, basically. What we're going to create is going to be this guy right here. We're going to wire him up. So this guy, I'm just going to put an A, and let's bring everyone's attention over here. A, because it's too much to write inside there. That node that we just created is a VOP Vex Surface Shop. Told you it was a mouthful. So a VOP Vex Surface Shop.
Which is a long name, but it tells you a lot about what we're going to be creating inside it.
It tells you an entire story, Steve. It's a container, but its purpose is to shade geometry. Notice it is a surface shop. That's the key thing to keep in mind, because there's all sorts of different kinds of shaders that we can construct. In this particular case, we are interested in getting color applied to geometry. And taking that a step further, we're interested in getting a simple texture applied to our geometry. So this guy is a container. So with him, let's go ahead and follow the arrow down. All right, that's awful. I surely can do a little better. Yeah. All right. So if we were to enter into this node, what we're going to find is simply going to be an output node. That's all. And the output node, whatever you wire into that output node, ends up traveling down this over here to the sub output, and that's what's going to be used back over on our sphere when we reference the material. As a matter of fact, I can go ahead and do this. This material, once we jump back up to the SOPS level, is going to simply reference this material right here, okay? Which now hopefully you can see the importance of the sub output. It's the response. It has responsibility of giving the final output of all calculations that occur from the shaders inside of the node. Excellent. So now let's jump down into our VOP Vex Surface Shop. That's this guy right here. All right. For this, I'm going to make a dividing line so that we all understand what's taking place below is occurring within a Vex builder. This is where we get to program visually. Okay, but remember, this is all happening inside of this guy. So in here, when we jump in, the first thing that we're going to get is an output node that's already there. And that output node is going to have several incoming connections. Let me just I'll draw 3 of them, and we'll talk about some of the different things you're going to find. You're going to find CF, you're going to find OF, you're going to find AF. I guess we can write him in too. Oh, wow, man, this stuff sounds complicated. What are we really looking at? Well, CF is just color. Our OF is going to be our opacity. AF, alpha. You'll also find surface normals in there, and a couple of other things. Now, this is really neat how this works. This is so simple. As a matter of fact, Steve, when you start putting all this together, demonstrate this. I want you to drop down a constant. And with that constant, let's go ahead and set the parameter type to color so that we can specify a color. And then we can just take this guy, take his output, and plug it in there and render.
Sure.
As long as we have made this reference right there so that we're referencing our material, the data is going to flow exactly how we want it to flow. This constant information is going to be whatever color we put in. It's going to come over here to the output. That information is then going to get passed over here to our sub-output, which then is going to be rendered on our geometry at render time. Okay, so the rendering engine is going to then cause this surface shader to calculate color information that will be applied to the pixels in your rendered image. Now, what is it going to look like? Let's say that you choose some cool color, like Side Effects Interesting Orange. So if you put orange in here as the color, I'll just write OR. When you render out your sphere, it's just going to appear as a flat colored circle, an orange colored circle. Why is that? Well, our lighting model right now is just constant. what does that mean? That means we're not taking into account all of our lights. We're not coming up with any sort of shading whatsoever to give a 3D representation. It's just a flat circle. That's all we're going to see, even though we all know it's a 3D sphere. Okay? That's because we need some sort of lighting model that's going to take into account the lights that are in the scene. And we've all heard of these lighting models, Lambert, or what if we want to use Blinn or Fong or anisotropic, etc. So where does all of that come into play? So lighting model is one of the things that's interesting that we're going to need to set up. We also need to set up the ability to work with a texture, because at the moment we simply have a constant node, and that constant node allows us to assign one color, but it's just one color. We need a texture that has been saved out into the textures folder that Steve has created. So once, Steve, you demonstrate this guy, let's take him back out. Let's show everyone how easy this really is. Steve is going to create a texture node. And this texture node will allow us to go out to our hard drive, find the texture, and set it up. Simple enough. Now, coming out of the texture node, we have a color output. So I'll just put C for color. If we take this color output and we run it over here into CF for the output, and we take our texture node and we go out to the hard drive and we select our character's texture, and now we render out, we're going to see two things that are interesting. One, our texture is going to be all screwed up. Okay? And of course, everybody who's watching this video immediately thinks, well, yeah, you have not assigned any UVs yet. All right? Well, that's 50% of the problem. You're also going to see that we still don't have any sort of shading occurring on the geometry that gets rendered. So even though we see variations in color, meaning we'll see maybe an eye or part of his hair or whatever, it's still going to be a flat circle with these variations of color within it, because our lighting model is not taken into account all of our lights to generate shading. So we'll get back to the lighting model in a second, but let's first deal with the interesting texture layout. We want the texture to be applied to our sphere in such a way that his eyes, nose, mouth, hair, all that aligns properly and looks right. At the moment, it's not. So again, as I said a second ago, everybody's going to think, it's because you need UVs. All right. So we're going to put a UV texture in. So just so that I don't have to redraw everything, let's just do this. I'm going to push the material down. And we'll all stipulate that our display is down here. And here, we've added in a UV texture. So we add in this UV texture node up at the SOPS level, and we hit render, and there's no change. It looks exactly the same, our rendered out flat sphere, as it did a second ago. We still have the texture colors, but there has been no shift whatsoever to these particular colors. Why is that? We've added in a UV texture node. Simple. Our shader has not been instructed to make use of the UVs that have been applied to the geometry up at the SOPS level. That's right, the shader needs those UVs. Now, hopefully everybody's starting to get a bit of a clearer image in their head why UVs are so important. We've already discussed that UVs are a coordinate system that is used to instruct a texture how it is to be applied to a surface, how it's going to be painted on. Okay? Well, our shader, which now contains our texture, has no clue how it's going to be applied. So we need to somehow bring these UVs into our shader and use that information. Well, you're going to find, of all of the different connections available on the texture, you're going to find two of them, one labeled S and one labeled T. Aha! Coordinate system. Basically, we can plug U into S and V into T, and we'll then have the coordinate information required for this texture node to know how it needs to apply itself. But how do I get this back here into here? That's pretty simple, actually. We can use a parameter node to import information found up above. And that's what we're going to do. When I say up above, I'm talking back up at the SOPS level. So we're going to bring in a parameter node. And Steve, I believe when we did the Houdini Fundamentals class, and we spent a little bit of time in Vex, and we were creating some really cool SOP-VOPs, that we did that. We imported some information. You remember what it was we imported?
We imported, I think we had a radius control, maybe a height control.
Yeah.
It was for our like helix.
Exactly.
Helix.
We imported that information down inside our VOP network. So let's go ahead and just put parameter up here. P-A-R, good enough. Parameter. And this parameter node has a parameter on the node called parameter name. This is very important. Casing is really important. We're looking for a parameter that already exists up in SOPs above us, called UV. It is a lowercase UV. If you were to type a capital U and a small v, or a capital U and V, that parameter does not exist above us because this is case sensitive when working in Houdini. So we will set the parameter name, so our PAR name on the node, to a lowercase uv. The moment we do that, this node right here is reading the information that's up here, okay, that's being generated by that particular node. Excellent. Now we have information, and we can take the output of this parameter node, and we need to use it over on our texture node. Oh, that's good, but the texture node takes in 2 connections. We have 1 connection coming out. The connection coming out of the parameter node is a vector. It contains 3 floats. These guys are individual float inputs. So, fortunately, we happen to have a vector to float node that we can use to take an incoming vector and split it out into 3 floats. So we're going to throw one of those in. So I'm just going to say vector to float. Excellent. 1 input, 3 float outputs. So we'll simply connect that up. So now the information coming into the vector to the float is split up into 3 different floats. We wire the first one into S. We wire the second one into T. We don't need to worry about the third one because we don't need that. We just simply need the U and V coordinate information. That information is now being passed into our texture node. Our texture node now has the information it needs to apply itself properly to the geometry above. Outstanding. Now, if we render, things look much better. In fact, at this point, Steve can change whatever kind of UV coordinates are being generated by jumping back up to the UV texture node and playing with those parameters, and he can get everything set up so that our texture is now being applied to our sphere properly. But we still have a problem. We have finished that one, but the lighting model is still flat. It's still a constant lighting model. We're not taking all of our lights into account to generate any kind of shading and specularity. So let's look at both of those. Let's start out by looking only at just getting some shading. So what we're going to do is use a Lambert diffuse Vex node. This guy will take into account all of the lights in the scene, and as our sphere, so here's our sphere, and as he gets rendered, each of these pixels that are getting rendered out, basically the rendering engine is going to say how much light is striking this, so how many lights are involved, let's add all these lights up, all right, we've got this much light. And now this Lambert diffuse Vex node will take that information and calculate the intensity of the diffuse color that's going to be used on each of these pixels. Now, obviously, this lecture can get much deeper, and I could even have Steve have a great time and whip out some math to show how the Lambert model is actually using all of these numbers, but we're not going to go that deep. We're going to keep things simple. As long as you understand the big picture is that at render time, a pixel is getting rendered. I mean, yes, we have a 3D sphere, but come on. Our final rendered image is a flat picture. That flat picture consists of nothing but a bunch of colored dots. The rendering engine needs to generate the color for a dot. So that dot may just happen to be part of the sphere. So it looks at all of the lights, it calculates the intensity of the final light that's striking it, and then it takes a look at the lighting model and it uses whatever algorithms have been established within that lighting model to generate the final color and the intensity of that color that's going to be used. So, is that all right, Steve?
That sounds fantastic.
All right, let's go ahead and I'm going to go ahead and erase all this guy out too, because we're about to change this up just a little bit. So what we're going to do is we're going to bring in that Lambert node. We'll throw him in here. And with the Lambert node, it has a color output. So I'll just put C, I believe it's CLR. And we'll take that color output and we'll just plug it up over here into CF on the output node. Now, obviously, at this point, we're not taking into account our texture. You'll notice the connection back here has been broke. Well, of the different inputs, one of the inputs that we have is DIFF for diffuse. So what is going to be driving our diffuse color? Our texture is. So we'll simply take our color and we'll plug that guy into diffuse. Now if we render out, we no longer have a flat circle with the colors on it to indicate our talented ball. We now have a shaded sphere sitting there with the texture properly applied for our character. That looks fantastic, and we could stop here if we did not want any sort of specular highlight on our geometry, but it'd be nice to have our ball kind of shiny. You know, he's been polished up and all. He wants to look good when he goes out there and presents. So how do we get specularity involved in the shader? Oh, it's so simple. There is another Vex node that we can grab that is called a specular functions node. And the specular functions node provides several specular algorithms that we can use. And once again, this node is taken into account the pixel that's being rendered, how much light is striking it, the angles, so that we can then generate, based off surface normals, etc. So when I talk about angles, we're talking about normals and all. We can generate what kind of color is going to need to represent that particular pixel based off all these lights, such that it's going to look like a specular highlight. But in the end, specular highlight, everyone thinks, ooh, shiny. Come on, it's just a color. In the end, that's all we're looking at, it's just a bunch of colors. So we'll bring in the specular functions, and we'll just put specular. And on the node, we have the ability to select what function we want to use. Is it going to be blend? Is it going to be Phong, etc.? You'll notice that we're not needing to input our texture or anything into it for the simple fact that he's just going to take into account light, angles, etc. and generate a color that's going to represent, in our case, a circular specular highlight.
Exactly. It's just going to use a single specular color as opposed to assigning a texture map for specular color.
Exactly. Now, how do we get that guy into there too? That's our final problem. We're almost there. Well, it's real simple. We just need to add the two colors together. That's a color coming out of there. And even though we think shiny, it's just a color coming out of there. We don't want to multiply. And here's why. Let's think about the specularity. What if the specularity happened to be being calculated on a side that no light was striking, but let's say you could see a little bit of the diffuse. Let's say you were using some ambience in the scene so that it wasn't completely black. Let's say that specular itself was 0 or even near 0. Do we want to cancel out our diffuse color thanks to specularity's color? No. We want to simply add these together. And Steve, if you want to spend just a second and talk about how that's how lighting is calculated. Color is calculated in the end when you have these different elements, ambient, diffuse, specular.
Yeah, exactly. When you have a lighting model, the mathematical lighting model that these FOPs are based upon, and you have combinations of ambient, diffuse, and specular, they're simply added together. That is just the way that they're combined. So it makes sense for us to add these two guys together here.
Oh, if you multiplied them on him, he's using ambient, and there was no ambient.
Everything would be black.
Now everything is black.
Yeah.
So we obviously don't want to multiply. So, fortunately for us, there's an add node. And we'll take input 1, and let me go ahead and, is that going to actually work? No, I didn't think so. My eraser on Wacom tablets almost always die in the middle of a video. It's interesting. So we'll take this guy. We'll put him into the first input. We'll take this guy. We'll put him into the second input. Of course, we have a sum output. We take the sum of those two, and we plug that into our CF of our output node. Now, when we render out, we see what we're looking for. We see a shaded ball with the character texture applied. and we see a specular highlight if we create a light in the scene and position it in such a way that we should see a specular highlight. On this guy, we have the ability to set more than just what function we want to use. We also have things like the specular rough, but there's several different parameters that we can make use of on that node. So I just wanted to point out that that node provides more than just what function do you want to use. We also have a series of parameters that allow us to define the characteristics of the specularity when applied to our geometry. Ta-da! We have just created our first very simple custom shader. Very lightweight. You'll notice we don't have a bunch of parameters that are completely irrelevant to the job of this shader. This shader's job is simply to allow a texture to be properly applied to geometry and to drive the diffuse color, and then just to have kind of a global specularity. And we have established that with this custom shader. Again, this custom shader exists inside of the material node that we created inside of our ShopNet manager. And that material node, again, I'm talking about this guy back over here, is being referenced. I guess I could update that just so that the final picture looks, accurate. He's being referenced by our material node down here. So that is our mission in this video. Steve, is there anything you want to add to the theory before you jump over and start putting it all together?
No, I'm very happy with the theory so far.
Fantastic. All right, so with that, we're going to jump over into Houdini and get all of this set up.
All right, so let's go over into Houdini.
Wait a minute. Before we go over to Houdini, there we go. Well, we finished talking about the lighting model, so I figured I might as well check it off.
Sure, that's awesome.
You know what, thinking about the lighting model, I'm not going to draw it in here, but you spend a second talking about how the diffuse, the ambient, specular, all of these components are added together. Let's do that.
Yeah, let's
because right now we're not
then.
taking ambient into account when we create our shader. Let's make this one step more complicated.
Sure.
What do you think?
Yeah, that sounds awesome.
You are the man, Steve.
Fantastic.
Okay, now over into Houdini.
Cool.
Had to check off the lighting model. Come on.
Yeah, definitely. So we're currently down looking at our stage assets. So I'm going to push U to jump back up to object level.
Okay.
And I'm going to create a new geometry node using the tab menu. So enter to grab that, enter to place it in. I'm going to rename this guy to character. And then push enter to jump down inside and delete out our file.
Okay.
So now we can create the sphere that's going to be the basic geometry.
That was some challenging modeling.
Oh, yeah.
Good job.
Which I'll rename to character sphere, and I'll set this guy over to NURBS.
And at this point, I'd like to focus everyone's attention on the following. We did not talk about setting up expressions so that radius for X, or excuse me, Y and Z are being controlled by X. We also didn't talk about moving this guy up so that he is sitting on the grid floor. The reason is, as we progress further and further into this training series, there's no reason for us to really go back over stuff that we have whiteboarded out and we've talked about. If we did that, this would end up being a very long series and a lot of redundant information.
Exactly.
So we just figured that when we get to things that have already been talked about, Steve's simply going to do it. He's going to talk about why he's doing it, and he's going to show you the result, but everyone should be comfortable with what he's doing.
Cool. So I'm going to hide out all of our other objects just so that we only look at our sphere. I'm going to space H to home up on our sphere.
Let's go ahead and turn the grid on real quick.
Cool. So currently he's centered up about the origin. We can change our center Y to take our radius Y, and now we'll sit up on the construction plane. I'm also going to set radius in Y to reference rad X, and radius in Z to reference rad X.
That way we just change one parameter.
Exactly.
Since
we
want
get a perfect sphere.
Yeah, we want this guy to always be a perfect sphere, unless he's squashing or stretching, but that will be handled by other nodes. Okay?
Fantastic. So we know we're going to assign a material to this guy, so let's right-click on the output, type material, enter to accept that, enter to place a material into the scene. We don't yet have our material, so let's create our shop network where we'll be able to build our material. So tab, shop network, enter. I'm going to rename this to character shop. And then jump down inside by pressing enter. And now we're in the shaders context.
Interesting how Houdini re-showed everything. See if you can say show all and hide all. I'm just curious. Over in the viewport. Just how we're seeing everything. Okay, nope.
Weird.
Yeah,
And
again, still working with 9.5. So
the fact of the matter is we're not going
no
to
longer
see any of our changes at shaders
That's
until we
true.
render anyway, so it's
doesn't
not
matter.
the end of the world.
I was just curious.
Yeah, it's kind of crazy. So I'm going to push tab because we need to create that material, our container for our shaders. So I'm going to type material and push enter. We can see now we have a material shop, which I'm going to rename to m_character.
So it's just our container.
Yeah, it's
for
just
shaders.
a container in which we can create our shaders, and here's that sub-output node where we wire the output of our shaders into to get the shader output out of our material.
That's right. And of course, you just hit enter to drop down
Yes, I
into
did.
the material node.
Cool. So I'm going to bring up the tab menu again, and this time we're going to create our shader, and our shader is the VopVex surface shop. So I'm going to type Vop Vex surface.
You want to
There
show
we go.
them? There's a whole bunch of different ones that are available.
Yeah,
Since we're dealing with the Mantra renderer and it's
So here's
surfacing.
there's a VopVex surface shop, but if we were to go to Mantra for say displacement, there's a VopVex displacement
Nice.
shop, etc., etc. So let's grab our VopVex surface
Yep.
shop. Single left click to select him, enter to place him into the network. I'm just going to leave him named Vop surface 1
Sure.
since our material is named our material.
So we can go ahead and wire it up.
So I'm going to single left click on the output of our surface shader and wire that into the next input, which wires that into our sub output. So now if we jump up, our surface shader is now coming out of our material. Fantastic. So I'm going to jump down inside our Vop surface by pushing enter, and we can see we've got our output for color, opacity, alpha, normals, etc.
And we are dealing with the Vex builder now.
Exactly, and we're only going to be worrying about the color output. So let's do the example where we just wire in a constant, set it to a constant color, get that assigned, and then see
Render
that
it out.
applied to
Yeah,
our
sounds good.
sphere. Fantastic. So I'm going to bring up the tab menu again, type constant, push enter, and enter. And we're dealing with a constant type that's going to be a color. And if we come over to the color tab, we can set the default color to some kind of side effects Houdini orange. And I'm going to wire the output of this color into the color output for our shader. And that's going to take this orange and feed that out as the color that will be applied when we assign this shader. So I'm going to jump up by pushing U, up again, and up again until we're at SOP level. I'm going to bring our visibility down onto the material, and I'm going to bring up the browser next to our material. And I'm going to jump inside our character shop and grab that material we created and make sure that we export a relative path to that material. So now we have our shader assigned to the sphere. We're not going to see any effect in the viewport, but when we render, we're going to see that we have a solid orange circle.
But that's the key thing. Solid. Constant lighting model.
Exactly. So we've got a solid color. Now let's get it to the point where we have a texture, but again with constant lighting.
Okay.
So let's jump down inside both our shop by double clicking, and inside the material by double clicking, and inside our VopVex surface by double clicking. I'm going to just nuke out that constant because we don't need him anymore, and replace him instead with a texture Vop. And the texture Vop has a number of inputs as well as a number of parameters. And we're simply going to set the texture map to point to our character texture that we have on file. So I'm going to bring up the browser, and I'm going to jump up to the project folder that has OTLs, scenes, textures. Inside the textures folder, I have a ball character.tga file, which I'm going to accept. And that file, we're just worried about RGB. We don't need to worry about alpha, so I'm going to leave the signature set to RGB. So this texture takes in that file, and it's going to output the color from that file, so we can wire that output through. And obviously at the moment we haven't wired up S&T, so we're not controlling the UVs. So when we render, let's just jump up to SOP level. When we render, we're going to see our texture is applied, but we don't have any control over how it's applied. It's applied at the moment in this default manner that we have no control over. And even if we were to close out that render and wire a UV texture after our sphere, so I'm going to right click on the output of the sphere and wire in a UV texture SOP and push enter to create that. You can see we should have now created UVs. If we middle click on this guy, we can see that point attribute UV. And we're creating a orthographic texture type. We know that that should look like a projection down in Y. If we render out, our UVs haven't changed.
Yeah.
We are not getting an orthographic projection. So this guy is being ignored. He's not being taken into account. And we saw on the whiteboard why that is the case. If we jump back down inside our shop, inside our material, and inside our VOP network, we need to drive SMT with those UVs, and to do that we need to bring in the UV as a parameter. So I'm going to push tab to bring up the tab menu. I'm going to create a parameter VOP, enter to accept that, enter to place that into the scene. And the most important parameter up on here is both the parameter type, we're dealing with UVW, which is a 3 float vector, and the name, UV in lowercase, which, let me just jump back up to SOP level. You can see again when we middle click UV in lowercase. So back down on this parameter VOP, I'm going to rename the parameter VOP to UV import, and I'm going to give it a label of UV coords. But the most important thing is the fact that we're dealing with 3 floats, because that is the data type of our UV parameter, and the fact that the name is UV in lowercase. And we can see we've got a vector coming out of here, and we need to deal with the floats. So let's split this into its 3 different float components. So I'm going to right click on the output, and I'm going to wire this into a vector to float. Push enter to accept that, enter to place that into the network. And now we can take our U component and wire that into S, and our V component and wire that into T. And now if we render, we'll see that our UVs are taken into account. Whoa, explosion. Just give me a second. Alright, I can see the issue. We've got an underscore here on the end of UV, and that actually means
there's a space.
We put a space in the parameter name, and if there's a space in the parameter name, our parameter name is not UV anymore.
Actually, I think that was a wonderful demonstration of if the name's not right, you're not going to import the correct information.
Exactly. So now we've corrected that issue. I just have UV. You can see the underscore has been removed. And if we render this out, we're going to see our texture, and we can see that it is getting that orthographic Y projection, almost as if we take our texture and slice it through our sphere.
Demonstrate the case sensitivity.
Yeah, sure.
As well.
So again, we saw putting a space in is going to mean that we don't bring in our UVs. If we call it UV with capitals, then we'll see that again, we don't bring in our UVs, because this isn't the UV parameter. The UV parameter is UV in lowercase.
Okay, nice.
Fantastic.
So let's go ahead and fix our UV.
Yeah, exactly. So I'm going to push U to jump up to our material, U to jump up to our shop network, and U to jump up to SOP level. And instead of using an orthographic projection, I'm going to use a polar projection, which if we re-render...
Hey, we're looking at the back side of our ball.
Fantastic. So let's tumble our view around and render to see the front of our character.
Notice how we're still using constant lighting.
Exactly. We have no variations in terms of shade. We just have variations in terms of our color, in terms of texture.
Exactly.
So let's now jump down into our shader and implement our lighting model.
Okay.
So I'm going to jump down inside our character shop by pushing enter, inside our material by pushing enter, and inside our VOP network by pushing enter. So we've got our color coming out of our texture. So now we need to use this color as a component in our lighting model. So let's push tab and drop in a Lambert VOP. And the Lambert VOP allows us to take our color, and we can wire that into the diffuse color for the Lambert, and take the output color, which is going to take into account our lights and the positions of our lights and in relation to our surface, and take that illumination and take that into account with our color map and give us a color output. And we're going to take that final color output and use that now as the color for our shader, which if we render, we'll see that we do now have variations in shade as well as variations in terms of our texture's color.
Outstanding.
So that's the Lambert. We also would like some specular color. So let's drop in a specular VOP. So enter to accept that, enter to place that into the network. And with the specular VOP, we have access to which type of shading model we want to use. I'm going to leave that set to Vex Specular. We have access to specular intensity, specular color. Specular color works just as before when we saw on the Vex Super material. Mm-hmm. The specular intensity acts as a multiplier of that color. And U roughness works like the specular rough that we saw over on the Vex Super material. V roughness isn't taken into account unless we're using an anisotropic shading type, and sharpness isn't taken into account unless you're using a glossy shading type. So we're on Vex Specular, we only need to worry ourselves with these top 3 parameters. And you can see the outputs of our specular. Let's make this full screen for a second. We have the color output from our Lambert, and we have the color output from our specular, and we need to add those together so that we can take both of these colors, add them together for our output. So I'm going to right click on the color output of the Lambert and insert an add between this color output and the color input. So I'm going to right click actually on the output. I'm going to type add and push enter to accept that, and enter to drop the add in place. I'm going to rename this to add color.
Okay.
I'm then going to take the color output of the specular and left click on it, and left click on input 2 of the add, and that's going to wire the color output from our specular into the add as well. So now both of these will be added together. Their result is now being fed to the output of the node. And to make this nice and clear, I'm going to drop a light. We'll talk about lighting in the next volume, and we've talked about lighting very briefly in fundamentals, but I'm just going to drop a light in place so that we can see a distinct specular highlight when we render. And there we go. So now we've got both our diffuse shading that we can see over here, but also we're getting a specular highlight caused by that specular VOP.
Okay, very nice. So ambient?
Yeah, so let's delete out. We can leave the light in place. That would be great, because now we've got a side that isn't in illumination, and we'll see that have effect when we create our ambient light. So I'm going to jump down inside our character's geometry, down inside the shot network, inside the material, and inside our VOP network. So we've got our Lambert, we've got our specular, and we currently aren't taking into account ambient. And we could show that. We could drop in an ambient light and show that it's not boosting the dark areas of our object. So let's create an ambient light, which has a light intensity of 1. It's going to affect the OpenGL view, obviously, because OpenGL does take into account. But when we render, look at that. This guy is still in pure darkness. He's not receiving ambient light information. And that's because our shader doesn't take into account ambient light information. So let's jump down inside our character, inside the shop network, inside the material, and inside our VOP network. And we can create an ambient VOP and enter to select that, enter to place it into the network. And now we have another color output coming out of our ambient. So this ambient is going to take an ambient color, which we can set, currently is set equal to 1. I'm actually going to take our texture map and wire that into the ambient color, because I want the ambient color to correspond to the color of the surface, and the color of the surface is defined by our texture map. So we can take our ambient color, and it's going to take into account the basically the lighting information, the ambient lighting information, and we can take that color output and add that together with the other colors. Now if we render, it's still not going to work, and that's because our ambient intensity is currently set to 0. But if we were to boost this, I'm just going to boost it all the way to 1 to make this very apparent. There we go. So now we're taking into account our ambient lighting. Our ambient lighting is being multiplied in with our color texture, and the output of that is being added to both the output of our diffuse lighting model and our specular lighting model. And the final sum of those 3 lighting models is our final color for each pixel.
Very nice.
So before we leave, I do want to just point out one other VOP that kind of does combine all of these 3 guys together, and that's the lighting models VOP. So I'm going to push tab, and I'm going to create a lighting model VOP. And the lighting model VOP is really simple to use. We have the ability to select from our shading model. Constant would be like before we even had Lambert in our network. It just takes the color and it feeds the color out of the output. Lambertian takes our diffuse color, multiplies it in with the Lambert lighting model to give us a color. And then we have various specular lighting models. We have access to ambient colors, diffuse colors, specular colors that we can wire texture maps into if we wish. We have our UMV roughness again. So all of these get combined into this one VOP that we could wire our texture map into, and then wire the color output, as I rename things crazily, wire the color output into our outputs. But for demonstrating the 3 components separately, I chose to go with this route, so I'm going to delete that guy out.
Okay. There's one more thing I'd like for you to do. It's a cleanup thing.
Okay.
invisible.
Yes. Yes. We brought in our UVs, and this is great because it shows another parameter when we're dealing with a parameter VOP. We brought in a parameter called UV. If we jump up and look at our VOP surface, UV coords, that label that we gave our parameter is here, but it doesn't make sense to set UVs by typing in a number because it's a parameter that's bound to our surface and is different on each vertex. So we can jump inside our VOP network and we can check this toggle that's invisible on our parameter VOP. And what that's going to do is, oh, I jumped up one too far. It's going to make it invisible to the artist, but it's still bringing in that information. So if we bind UV as a parameter onto our geometry, then that parameter gets taken into account, but it's not a parameter that we're going to see up on our shader that we could set manually.
Very nice.
Cool.
And with that, that's pretty much everything that we set out to accomplish in this video. We got the complicated task of modeling our character out of the way. Fortunately, it was just a single node. And set up some expressions to make sure that radius y and z always stayed the same value as radius x. And then we made sure that our ball is sitting on top of the construction grid. And then we created our own custom shader that was inside of a material container that you created. And very simple shader. We walked through what all of the different nodes are doing. And with that, that wraps up this video. Thanks a lot.